Hi, it's time for another math easy solution. Turn to discuss further into differential equations and look further into separable equations and go over example 3 of the example series and solve this one, which states solve the equation y prime equals x squared times y. Well, to do this, let's first look at rewriting this in terms of Leibniz notation, or in other words, write this as dy over dx equals to x squared y squared. This is just because we're used to this. And also recall from my separable equations video, we can basically rearrange this so that we'll have all the y's on one side, all the x's on the other. But in this case, if we do that, if we divide by y and then times by dx on both, so we move these around, we get a 1 over y dy equals 2 x squared dx. Except this 1 over y, it's not defined when it's when y equals 0. So to solve it this way, we have to impose that, well, y is not equal to 0. So this is for the case y is not equal to 0. We can solve it like this. And now what we could do is take the integral on both sides. So we get a 1 over y dy equals 2 integral x squared dx. And then solve this integral of 1 over y. dy is simply, like I showed in my earlier video, ln of absolute value of y. Again, you can see the proof for this in the video link below. And again, you have to add a constant plus c1 equals to here. This is x3 divided by 3 plus a constant c2. And I'll just combine the constants. So what we'll end up having is ln absolute value of y is equal to, and we'll go x cubed divided by 3 plus, we'll call this constant c, where c is simply c2 minus c1. That's just, again, we're just subtracting the constant, move this over to this side, and when you subtract constants, it's still a constant. Let's call that c. And now what we have is this implicit formula, but we can actually still solve this, and to do that, we could solve this for y explicitly. We could do this by taking the, or not taking the, by basically making both sides a power of e. So what we could do is write this as e to the power of ln y. So we're doing this on both sides, we're not changing anything. This is x cubed over 3 plus c. When we make it a power of the exponential number e, what we have here now, and also e ln absolute value of y, and recall from my logarithmic properties video, or this natural log, this e, this simply becomes the value inside the ln function, which is going to be absolute value of y, and this equals 2. And this one we can write this as e to the power of c times it by e to the power x cubed, because it's the power. So this is the addition of powers is the same as multiplying powers like this. And again, you can learn more about this this addition of powers in my earlier videos on power functions, and you can see that in the video link below, as well as other related videos to this video. So anyways, so now we could, this is an absolute value, so this just means that this has to be positive. So what we could write this as is y is equal to plus or minus e to the c times e to the x cubed divided by 3, and it's plus or minus because, well, doesn't matter if it's plus or minus, and we put this in here, it's going to be absolute value, it's going to be positive. And again, basically because of this absolute value sign, if y was negative, the absolute value would make it positive. We'll still make it this equation e to the c times e to the x cubed divided by 3. So this is our solution, and again, this is for y is not equal to 0, so that's the case. But what we can do is check if y is 0 is still a solution of the differential equation. So I'll just write check if y equals 0 is a solution. Because again, the method we used to get to this point, we assumed y is not equal to 0 because we had a 1 divided by y in the equation. So check if y is a solution. So y equals 0. If that's a solution, the derivative has to be, well, y prime is equal to 0. And now let's look at our starting differential equation. Y prime equals x squared times y. So we have y prime equals x squared times y. And then if we plug in 0 inside here, we get, well, x squared times 0, which is just 0. So we have y prime is 0. So this matches, and there's a y in there. So again, this is a solution. So thus, y equals 0 is a solution. So since it's a solution, what we can do is rewrite our solution here. We got this e to the c. Again, e to the c is still a constant, and there's a plus or minus. So thus what we have is the general, let's write thus general solution. We'll write it and combine all of those constants into one. So general solution is just y equals to a times e to the x cubed over 3. And there is our answer, where basically a is just a constant. Where a equals to arbitrary constant, and then we have basically 3 cases for those to be exact. This equals to plus e to the c, or it could equal to minus e to the c, or equals to 0, depending on basically if you want to be exact, 100% complete based on the derivation here. But at the end of the day, these are all constants. So again, it could equal any one of these or any other constant, and it will match with basically both derivations. This is this equation, and also that y0 is still a solution. And now what we can basically do is, if we were to graph the direction fields, like this is y-axis again, like I done before in my earlier videos, I'll go over the calculators that I used to go over these. Basically, this is the direction field for this, for the differential equation. So I'll write this down. Direction field, direction. So this is the direction field for our y prime is equal to x squared times y, and as you can see, it looks like this. And these are the solutions. These are the solutions to basically solutions to this differential equation, to y prime equals x squared times y. Whoops, I don't know what happened there. But anyways, these are solutions where with different coefficients, different constants a right here. So these are y equals to a e to the x cubed divided by 3. And for here, as you can see on these equations, this first one is 5 times e to the x cubed divided by 3. This is going to be, so this red one, that's in red, a equals to 5. And then this orange is a equals to 2. This one is a equals to 1. This right here is a equals to -1. And then the final one here is a equals to -2. And as you can see, it looks like this. But now if we compare the direction field, which is again just slopes numerically calculated from each, basically at many points through using this direction field without actually knowing the solution. But as you can see here, if we start off somewhere like this and try to follow it this way, we follow the direction field, it becomes a similar equation, similar curve to these two. And also going further goes something like this. So again, it matches it pretty well. If you start up higher and then follow it, it looks something like this. Let's just go down on the bottom side. As you see, this just matches it. Just want to show it just for clarification purposes, and it goes all the way down. If we go higher, it goes like this again, and it goes down as well. As you can see, you could just follow these, and then you'll get these exact solutions right there. And again, they match pretty well. And the calculators I use for these, this one over here is how I graph that. Just type in x squared times y, and you get this equation. And then the graphing one, I use this one. This can also graph implicit equations like I showed in my earlier video. And then here is the link. When you click link to this graph, it shows what I drew here, which is pretty cool. And you can add as many equations as you want. And yeah, this is probably the best graphing calculator I've seen on the web. Anyways, that's all for today. Hopefully you learned from this example how to get the solution, and also how to basically deal with constants of different types, like the C2 minus C1, it's still a constant C. This plus or minus e to the C is still a constant. Y is 0. You could still have the constant 0 is still a constant. So you could add these all and loop them all together into one giant constant A. And then as you see, the direction field and the solutions match up pretty well. Anyways, that's all for today. If you learned, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.